Rotational motion can be defined as the motion of an object around a circular path in a fixed orbit. The dynamics for rotational motion are completely similar to linear or translational dynamics. Many of the equations for mechanics of rotating objects are similar to the motion equations for linear motion. In rotational motion, only rigid bodies are considered. A rigid body is an object with a mass that holds a rigid shape. Simple examples of rotational motion include a ceiling fan, spinning top, rotating blades of a windmill, etc. To understand the theory of rotational dynamics, it is necessary to get familiar with key terms that appear in the equation of rotational motion. The center of gravity is a theoretical point in the body where the body's total weight is thought to be concentrated. It is important to know the center of gravity because it predicts the behavior of a moving body when acted on by gravity. In the figure, a person's weight is being balanced by the weight of the children. The location of the center of gravity is governed by the equation m1r1 equals m2r2. You can observe that it is easy to locate or calculate the center of gravity of regular symmetrically shaped objects like cube, cone, square, rectangular, triangle, etc. Then what is the center of mass? The center of mass is a point at which mass distribution is equal in all directions and it doesn't depend upon the gravitational field. The center of gravity is a point in an object where the distribution of weight is equal in all directions and it does depend on the gravitational field. However, an object's center of mass and center of gravity lies at the same point in a uniform gravitational field. If 2-point objects of mass m1 and m are connected by a weightless rod of length r1 plus r2, then the location of the center of mass can be derived using mass distribution formula. If the object is in the shape of an equilateral triangle, then the center of mass is 1/3 the height from all the three faces. For a semicircular disk of radius r, the center of mass is located at a height of 4r by 3 pi from the base of the disk. And for a half ring, it is 2r by pi from the base. For a solid hemisphere, it is at a height of 3r by 8 pi from the base. If there are n number of point masses distributed as shown in the diagram, then the location of the center of mass can be calculated from the standard formula. XCM equal to sum of m1 r1, m2 r2 up to m n r n divided by total mass. What is rotational motion? We know that when a body moves in circles around a fixed axis or a point, it is said to be in rotational motion. When a body moves in a rotational motion around a given axis or a line, that is at a fixed distance and fixed orientation relative to the body is rotating around the axis. For example, when we open a door, it turns around the hinges. When a body moves such that it rotates around a single point and not an axis such as a spinning top, it is in rotational motion around that point. But what causes rotational motion? Force is responsible for all motion that we observe in the physical world. The force responsible for rotational motion is called torque or the moment of the force. In rotational motion, we have certain variables called the rotational variables. The different types of rotational variables are angular displacement, angular velocity, and angular acceleration. In rotational motion, we rarely deal with linear displacement. Instead, we use angular displacement. When the object moves from position P to P1 along a circular path, the line joining the initial position of the object to the center of the circle sweeps an angle of theta when the object reaches position P1. This angle theta is called angular displacement and is denoted by theta. When the object moves from position A to position B along a circular path, and if the angular displacement is delta theta in a very short interval of time delta t seconds, the angular velocity is equal to rate of angular displacement with respect to time and is denoted by omega. On similar lines, if the angular velocity at the position A is omega 1 and at the position B is omega 2 in a short interval of time delta t, the rate of angular velocity with respect to time is omega 2 minus omega 1 divided by delta t, which is equal to delta omega divided by delta t. The rate of angular velocity is called angular acceleration and it is denoted as alpha. The kinetic energy of the moving along the circular path is calculated using the equation for kinetic energy for linear motion at any position. So kinetic energy equals half mv square. But the velocity of the object can be expressed in terms of angular velocity as velocity equals radius times omega. Substituting the value, you will get kinetic energy equal to half I omega square, where I is called moment of inertia, which is equal to mr square. There is a lot of similarity between linear motion and rotational motion. Displacement is compared to angular position, velocity to angular velocity and acceleration to angular acceleration, mass with inertia, momentum with angular momentum, and so on. Let us try to solve some questions to understand the concept of rotational motion. In the question, there are two particles are placed at different positions in x-y coordinate system and their masses are given. You are required to find the center of mass of two particle system. Calculate the center of mass using standard equation for x and y axis separately. If the position of the objects is given in 3D space, then calculate center of mass about z-axis as well using the same standard equation. In the second question, we have two objects. The first one is a uniform rod of length 10 meters and weight 20 kilograms. The second object is mass of 5 kilograms attached to the other end. The position of the center of mass from the hinge is to be calculated. In this question also, the same formula for center of mass needs to be used. The rod is modeled as a point mass with the distance from the hinge equal to half the length of the rod. In question number 3, the law of conservation of angular momentum is to be used. The total kinetic energy remains same. When an additional mass is attached to the spherical mass the equator, its inertia will increase and as a result the angular velocity should decrease to conserve the angular momentum. In question number 4, you are required to calculate the moment of inertia of a uniform rod of length L and mass m. Torque about the hinge is given by F into L, where F is the force and L is the length. This torque produces an angular acceleration alpha. Now torque equals I times alpha. Simplifying, we get moment inertia of the rod as F into alpha into L square. In question number 5, a circular disc is rotating about its axis. After applying a tangential force F, the angular velocity becomes 2 times omega. After 1 second, you are required to calculate the force F. Questions from 6 to 9 are for practice. Solution for each equation is given in detail. Please pause the video and go through the approach to solve such questions. We have come to the end of the video. Thank you for watching.